manage to relate to the student. This is like
Okay, class, that's good to have you back. This is the last lecture for the first semester. So after today, we are done. And if you are to pay very close attention, this is the most, I would say this is the most important part of the unit. And in this question, this topic comes every single exams, AP exam. You will have multiple choices. You can have responses on this topic. So listen carefully. You will be able to describe the form of the titration curves for titration of a strong acid by a strong base, a weak acid by a strong base, or a strong acid by a weak base. You should be able to calculate the pH at any point, including the equivalence point in acid-base titration. Your homework, you have Quest acid-base buffers. This is the last one. Okay, Quest acid-base buffers. You should have Quest 1 through 5, and then acid-base buffers, and have your lab report ready. Now, titration. What is titration? Titration is when a non-concentration of base or acid is slowly added to a solution of acid or base. Okay, so you know concentration of one of them, you use it to find the concentration of the other one. What is equivalence point? Equivalence point is the stoichiometric amount of acid equals that of a base, when the number of moles of hydrogen ion from the acid equal the number of moles of hydroxide ion from the base. All right, what is the difference between equivalence point and end point? End point, that's when you end the titration. The point of in a titration where the indicator changes color. So if you choose the right indicator, the end point will be the same as the equivalence point. Okay, equivalence points, moles acid equal moles base. End point is when you have that change in the indicator. Those are different shapes of pH graph. So, and if you are to listen carefully, you did a lab where you use your burette that has a strong base, and you use a flask or a beaker with your acid. If you have, you definitely, those are exams questions. They give you the graph and ask you to interpret it. Or they ask you to sketch it for a specific acid and base. So this is the way you do it. Your x-axis will be the volume of the base added, or the volume of whatever is in the burette added, and the y-axis will be your pH. There are 5 different points in a pH graph you need to know, and we want to see it in your lab report. 5 different points. In other words, there are 5 different types of problems you can solve with that graph. Number 1, you look at the beginning right here. This is the pH of the acid before any base had been added. So you look at it. If it's very low, that means you have a strong acid. All right, and then when you have that very drastic change in pH, you have that vertical line. To find the equivalence point, you go exactly midway that vertical line. Okay, so you have that big jump in pH. When you get to this point here is when you already neutralize all your acid, and then you have excess base. So the pH of that solution will depend on the excess base you have in that graph. So it depends on the shape. You should be able to know if you have titration of a strong acid versus a strong base, or a weak acid versus a weak base. For example, for this one, if you start at a high pH, that means you have the base in the beaker and you are adding the acid, and right here at the end you have your excess acid. So the pH will depend on that excess acid. Alright, let me now right here, the difference between the titration of a strong acid versus a weak acid. As you can see here, the strong acid starts at a very low pH, and right here where you have that flat part of the curve, and that's where you get kind of frustrated doing the titration, and you keep on adding base, and then you don't see any change in the pH. This is the buffer region. It is a buffer. So you keep on adding the strong base and the pH doesn't change. Alright, and then if this is a weak acid, like we said, it starts at a higher pH, and then this is the buffer region right here, and the vertical line is shorter for a weak acid. It is shorter. And here again, it doesn't matter if you start with a weak, but the excess will be your strong base. It will depend on the excess strong base. So you should be able to see the difference between titration of a strong acid versus titration with a weak acid. Now, here's another point that is extremely important in your pH curve, a graph. Very important. When this is the volume at for equivalence point right here. When you get to exactly halfway the equivalence point, halfway, you have titrated half of your strong base. At that point, the pH equal the pKa of that weak acid. Halfway the equivalence point, pH equal pKa. If you know that, it will save you a lot of time when you are solving problems with titration. Because if you know the volume for your equivalence point and you go halfway, you don't have to do any math. You just get the Ka of that weak acid, get the pKa, and then it is the pH. So it will save you a lot of time. Okay, this is, I already said, this is the buffering region. It is flat, where you don't have a big change in the pH. And as you know, if you have a weak acid versus a strong base, your equivalence point will not be at 7. Because a weak acid plus a strong base give you a basic salt, the equivalence point will be higher than 7. Okay, and let's see what else. If you have a diprotic acid or you have a triprotic acid, any polyprotic acid, you will have different bumps in that curve. So you have different equivalence points. For each hydrogen ion, you dissociate. Okay, so you have more than, it's a polyprotic, different bumps. So I need for you to pause the video right now, get your calculator, you get your packet. I'm going to solve only problems from that packet. Let's do it together. Okay, let me repeat. This is the most important part of the whole unit because it has all kind of problems here. I have 5 different types. Let's do it together. For the titration of A, you have 50 ml. 50 ml of what? This is 0.2 molar of what? This is a strong acid. With this is 0.1 molar NaOH, which is a strong base. Calculate the pH of the solution at the following selected points of the titration. First, they asked me to get the pH, to find the pH when no NaOH had been added. Like I said before, you should always imagine what you have in that beaker. Okay, so if you have your beaker here, and then you have your burette right here, this is your NaOH, you are adding a strong base. And then you have your HNO3 right here, your strong acid right here. And then if they say before any NaOH had been added, the only thing you have in that beaker is a strong acid. So you just have to find pH the way you have been doing for a strong acid. If I have 0.2 molar HNO3 strong acid, it will dissociate completely to produce 0.2 molar H plus. How do I get the pH? This is the negative log of my strong acid. Negative log of 0.2 equal negative log of 0.2 is 0.7. Okay, thank you. I thought you were correcting the 0.2. It is 0.7. Thank you. All right, and you are done. That's all you have in the beaker is a strong acid. Negative log of the H plus. Now, it says after 10 ml of NaOH had been added. 10 ml of NaOH had been added. Let me tell you, whenever you have a strong acid and a strong base, you have a mixture of both of them, go to moles. Don't deal with molarity at this point. You have to do stoichiometry. And to make a difference between equilibrium table and a stoichiometric table, I'm going to invent a different table. We will call it BCA. This is BCA. It is before, change, and after. And whenever you use that BCA, remember you are using moles and moles only. So let's go with moles. What do I have in that beaker? I have H plus OH minus. Yield, this is one arrow, stoichiometry, yield water. And my soluble salt, which is NaCl if I write the full equation. I do not really care about the NaCl. It is a neutral salt. The pH is 7. It's not going to affect this. So let's do stoichiometry. What do I have? How many moles of H plus do I have? It is 50 times 0.2. Give me what? How many millimoles? Let's stay in millimole. There is no need. It is 10. So remember, I have 10 millimoles of the acid in that beaker. And this is not going to change. It is already in the beaker. This won't change. Plus, how many moles of OH minus did I add? 1 millimole. It is 10 millimoles, milliliter, time 0.1. Give me 1 millimoles. What would happen with the change? This is my limiting reactant. 1 millimoles. That 1 millimoles is going to react. So I put minus 1. With 1 millimoles of my acid, they are going to react to produce water. I have an excess of 9 millimoles of the acid. 9 millimoles of the acid. Now, that means it's only that excess acid which going to determine the pH of that solution. So what I do, now I need to use the same formula. Let me take my 9 millimoles. Let me tell you common mistake right now. Divided by total volume. Students forget to do total volume. What is the total volume? It is, remember I already have 50 and I added 10. The total volume is 60 millimoles. If you want to convert, that's fine, but there is no need. Because millimoles can, I'm sorry, it is a milliliter. It is milliliter. So milli cancel out, I have moles over a liter. So what is 9 divided by 60 is, yes, 0.15. And okay, 0.15 molar, which is the concentration of my H plus. Just get the negative log of this. 0.824. Thank you. pH equal 0.824. 0.824. This is after you add that amount of base. So now they ask you after you add 20 ml of that base. 20 ml. We do the exact same thing. Okay, so to save time, why don't I just use that same table right here. What did I add? I add 20 ml. That 20 ml give me how many millimoles? 2 millimoles. And I take away 2 millimoles. I take away 2 millimoles, give me 8. Is that 8? 8 millimoles of my acid. So I do 8 divided by the total volume. It is 20 plus 50 give you 70. This is millimoles. This is 70 milliliter. So the concentration is 0.114, and we just get a negative log of that. Okay, the pH at that point is 0.942. Thank you. pH equal 0.942. Okay, let's move on. Okay, 50 ml of NaOH. 50 ml. Can we deal with this without the table? Without, okay. 50 ml. So we have, I say without, and I'm doing it anyway. This is H plus. This is H plus is how many millimoles? 10. Does not change. This is my OH minus. It is a 50 times 0.1 give me 5. Okay, give me 5. So this is minus 5. This is minus 5. So I only have 5. It is 5 millimoles of my H plus divided by the total volume, which is 100. 100 milliliter. What is 5 divided by 100? 0.05. What is the negative log of 0.05? Say that again. 1.30. This is your pH at that point. 1.30. Okay, 1.30. All right. So now 100 ml of NaOH had been added. Remember, we have 10 millimoles of the acid, and then the base is what? 100 times 0.1 give you 10 millimoles. What do we have in that beaker now? 10 millimoles of acid, 10 millimoles of the strong base. What is in that beaker? A neutral salt. Just a neutral salt. I don't need to do any math. It saves me by knowing that. So the pH is, it is 7 because it is a strong acid plus a strong base. The pH is 7. As long as I show that, I don't really need to do any math. Okay, how about 200 ml of NaOH had been added? I still have 10 millimoles of my H plus. Now I have 200 times 0.1 give you 20. Is that 20 ml of my OH minus? So this is, which one is the limiting? The limiting is the acid. Minus 10, this is minus 10. I have 10 millimoles. 10 millimoles of my base. So what is 10 millimoles over the total volume? What total volume do we have now? 250. What is 10 divided by 250 milliliter? 0.04 molar. What is 0.04? It is the concentration of my OH minus. So when I take the negative log of 0.04, what is that? 1.3 and 1.35. What is that 1.35? Concentration of your OH minus. This is not concentration. This is the pOH. But remember, they asked me for pH. It is 14 minus that pH. So we have to be really careful what is in that beaker. You cannot just plug a use formula without knowing exactly what's going on. So this one is the typical one. This one. That's where we really need to pay attention. Hydrocyanide gas, HCN, blah, blah, blah. It is a very weak acid. They gave me the Ka. If they give you a strong acid, strong base, not too bad. It is not too bad. But here we have a weak acid and with the Ka. This is my acid. Dissolve in water. If 50 ml This is a 50 ml and 0.1 molar HCN is titrated with 0.1 molar. This is a strong base. Strong base. I have a weak acid and strong base. Now, letter A. They ask you after what is the pH after 8 ml of 0.1 molar NaOH has been added. Let's go one step back. Even though they did not ask me what is the pH before any base had been added. Okay, so this would be the first type of problem in here. How about if they had asked me what is the pH before any base had been added? Yes, but this is a weak acid. Remember, it is a weak acid. So this is HCN. This is HCN. So I would have to do equilibrium. This is H plus Cn minus. I need to do a rise table. This is a weak acid. I need to do a rise table before any base had been added. So you need to know what type of problem to use at every step. Now, I'm not doing this one, but I need for you to understand. It is a rise table. Let's send it away. Let's go with number 8. Letter A. It say after 8 ml of 0.1 molar NaOH has been added. You have two different ways to solve this problem. Because it has a strong base, you would go to stoichiometry. You do BCA and you find the concentration of each species. But the shortest way is, because even though I don't have a buffer yet, but a buffer will be produced after I add that NaOH. After I add it, because it is limited, it's going to use some of the acid. It will be used up. I won't have any NaOH, but there will be some salt. Because I'm producing that salt with a weak acid, it will be a buffer. So let's use the buffer formula, even though we don't have the buffer yet, but it's producing that buffer. So this is a shorter way. Where the buffer formula you have learned is what? Concentration of H plus, that's the one and only one I ask you to use, equal Ka times the concentration of the weak acid over the concentration of the weak base. But remember, we don't have any weak base yet. We don't have any weak base. But the concentration of the weak acid is, what is the concentration of the weak acid? It is 0.1, even though I don't see it yet, but I know it's somewhere. Okay, it is 0.1. All right. The concentration of my acid is 0.1. The concentration of my base, I don't have any yet. Okay, I know in math you don't put a 0 in the denominator, but don't worry, just for now, for a second. Plus, remember I told you when you start adding a strong unit, since you are adding a strong base, let's just take it away from the acid, and then we are going to add it to the base. You take away from acid, you add to base. What are we adding? Now, there is one thing you did not call my attention on. Remember I said whenever you start adding, you need to go to moles. Don't use concentration. So I cannot use that 0.1. What is the moles of the acid? Yes, we can do millimoles. Okay, 5 millimoles. So it is 0.1 times 50. Give you 5 millimoles. Let me repeat. Whenever you start adding, make sure you go to moles. You have to, because you are changing the volume. So it is 0.5 millimoles of the acid, and then I'm adding. No, I said this is acid, and then we are adding base. That means we need to take away the millimoles of the base added. Take away. So what is 8 times 0.1 is 0.8. Is it 0.8? Do we really have only 0.5? Okay, so what is it? Okay, 5. It's not 0.5. Okay, so it is 5. This is 5 millimoles. We take away the millimoles of the strong base is 0.8 minus 0.8. And then we are adding 0.8 to the base. So what is 5 minus 0.8 is 4.2. This one is 4.2 divided by 0.8. 5.25 times the Ka. The Ka is 6.2 times 10 to the negative 10. Okay, so H plus equal, H plus, concentration of H plus equal what? 3.25 times 10 to the negative 9. And then we just got a negative log of that H plus. Okay, 8.49. The pH of, after we add that amount, 8.49. Yes, it is 8.49. And then you ask yourself, does it make sense? It is a weak acid. We are adding a strong base. It should form a basic salt, and that basic salt should have a pH greater than 7. Okay, let's finish this problem. Let's finish it. So we're going to have to come back to it. And since I already said this is the last one, let's finish it quickly, please. Okay, add the half point, the equivalent point, the equivalence point. They ask for the pH. How do we find what is the pH halfway the equivalence point? pKa. pKa, you don't have to do any math. You just get your Ka, get the negative log of it. It is your pH. Okay, so what is the negative log of 6.2 times 10 to the negative 10? It is 9.21. pH equal 9.21. Okay, at the equivalence point, what is the pH at equivalence point? What we need to do is, at equivalence point, the moles of the acid should equal the moles of the base. So what is the moles of the acid? The moles of the acid we already said was 0.1 times 50 give you 5 millimoles. It is 5 millimoles. Should at that point you have used 5 millimoles of the base also. So when you add that acid to the base, 5 millimoles, you are producing 5 millimoles of salt. You are producing 5 millimoles. Let me quickly write that equation. I think I'm going to reset everything because it's getting messy. So for letter C, we have used 5 millimoles of HCN and 5 millimoles of NaOH. If you write an equation, you have HCN plus NaOH yield, this is not equilibrium, it's stoichiometry, yield sodium cyanide plus water. Okay, we don't care about the water. Sodium cyanide is a salt. It is a soluble salt. Give you NaCN that will dissociate completely into Na plus and Cn minus. I do not care about Na plus. It is the cation of a strong acid. It is neutral. The only thing I really care about is the Cn minus. What is the Cn minus? Because this is a salt of a strong base and a weak acid, that salt is basic. If I say it is basic, now I'm going to write an equilibrium for that basic salt, which is NaCN minus equilibrium. Let me put plus water. If I say it is basic, I have to produce OH minus plus OH minus plus, if I take OH from that water, I have one hydrogen left that will go with my Cn minus, give me HCN. Now I need to do a rice table with that salt. So what is the concentration of that salt? I said I have 5 millimoles of that salt. Common mistake, students forget to divide by the total volume. The total volume. So I need to find the total volume. The 5 millimoles, I had 50 ml of the acid. 50 ml of the acid. But what is the volume of my NaOH I have added from that burette? See, if I say 5 millimoles of the base, 5 millimoles of OH minus, and I know the concentration is 0.1 times the volume. It has to be 50 also. It is 50 ml. That means the total volume in that for that salt is 100 ml. So I need to take that 5 millimole divided by the total volume, 100 ml. What is 5 divided by 100? 0.05. This is the concentration of my salt. And then I don't have any more. This is okay. This is gone. The same 0 initial. And you do your rice table. So this is minus x. This is plus x, and this is plus x. And I write my expression. I write an expression for KB because this is basic. It is KB equal the concentration of my OH minus. This is x squared. It is x squared over 0.05 minus x. And what is KB? Remember they gave you a Ka for HCN. So the KB is 10 to the negative 14 divided by that Ka. So what is 10 to the negative 14 divided by 6.2? 1.61 times 10 to the negative 5. So guys, can you solve for x for me, please? Since this is slow, why don't we neglect that x to go faster? Okay, x equal 8.98. 8.98 times 10 to the negative 4. This is the concent, and then you go back on the table. You say this is the concentration of your OH minus. So equal concentration of OH minus. We get the negative log of that number. The negative log of that number should give us our POH. .04, and then the pH equal 10.95. Does it make sense? We said yes, we have a basic salt in that beaker. So 10.95 is the pH of that salt. Okay, one more step, I think. At equivalence point, that's what we just did. Okay, I have 2 more problems, but because the video, can I just tell you what they're about without solving them? I will just tell you in 2 minutes. Use the figure below to decide which indicator would be best to use in the titration of ammonia and hydrochloric acid. Ammonia, weak base. Hydrochloric acid, strong acid. Weak base, strong acid will give me a basic salt. It's not true. What did we say? Weak base strong acid will give you an acidic salt. So I need to get an indicator that will change color in the acidic range. I cannot choose phenolphthalein because phenolphthalein starts changing color at a higher pH than 7. If I choose the wrong indicator, then I will be sitting there waiting for it to change in color, and it won't change color until after 7, which is after the equivalence part. Let me repeat. You need to choose an indicator that will change color in the pH range for that salt. If they give you a picture, what about if they don't give you a picture? Let me show you something. This is the last one. Bromthymol blue has a Ka of 10 to the negative 7. Is yellow, and this is its acidic form of that indicator, because indicators are weak acid and weak bases. That's what they are. And blue in its basic form. Suppose that you put a few drops of this indicator in a strongly acidic solution. Strongly acidic. If the solution is then titrated with NaOH, at what pH will the indicator change color? Let me just tell you, and I'm done. I need for you to always check the Ka of that indicator. They will give it to you. You need to choose an indicator that will change color close to the the pH and the pKa should be very close to each other. Get the Ka of the indicator, find the pKa for that indicator. It should be close to the pH of that solution you are trying to measure. If I need a pH of 5, I'm going to get an indicator that has a pKa close to 5. Plus or minus 1 would be okay, close to 5. Okay, I'm sorry I had to watch the last minute, but since I promised this would be the last lecture, I did not want to come back. So I hope you take your time, watch that video, we watch it. This is really the most important one. So study for your final and your next unit test. Be ready with your lab report. I will see you next class. Bye.